Hey, welcome back to Calculus. In this first part of section 5.4, I want to tell you about something called an indefinite integral. Cutting 5.4 into two parts, and this first part I think will seem pretty light on the palate. We've been working hard this week with Riemann sums, limits of Riemann sums, definite integrals. So I hope this video lecture feels like a chance to kind of catch your breath, catch up, solidify some of the notations. Not a lot of new ideas in this section, really just some new notation, some new language. Okay, so I'm going to tell you about this new notation and language. It's called an indefinite integral. We've been studying in chapter 5 so far something called definite integrals, things that give us areas, net areas, distance traveled, displacement, and so on. So I want to tell you about what I mean by an indefinite integral. Well, we already know a bunch of them. We're going to look at a big table of them that's on page 403 in your text. I've got that table included here in the lecture. And then I'm just going to do a bunch of examples showing how this notation scheme, this idea of indefinite integral, can be coupled with the fundamental theorem of calculus to compute integrals. Okay, so let's take a look. Let's recall the first two parts of the fundamental theorem of calculus. That's what I'm abbreviating here with this FTC, fundamental theorem of calculus. The first part of the fundamental theorem of calculus says that the derivative of an area function is the integrand. So if you kind of think about it in the sense of we take some function f and we integrate it, and then you differentiate that result, you just start with the original function back. So it's like derivative and integral are like inverse operations of each other. The derivative undoes the integral. All right. The second part of the fundamental theorem kind of says that they're inverses of each other in the other way, that if you want to compute a definite integral of some function, you can do it by evaluating any specific antiderivative here. So my capital F is just some function whose derivative is little f. And you remember our evaluation bar notation. It just means plug in the upper limit, B, subtract, plug in the lower limit. All right, so that's how we were computing those definite integrals. Compared to taking limits of Riemann sums, this method of computing definite integrals is basically effortless. If you know an antiderivative for the function little f, and you can do this subtraction, then you can compute that definite integral. Okay, so it's because of that relationship. It's because of that relationship between integration and differentiation that we're going to switch our notation. We've already talked about what I mean by a general antiderivative of a function. It's a family of functions, any member of which has derivative little f, yeah? And we've just been denoting those antiderivatives by capital. So the capital F is an antiderivative of little f. I have it written down here again. So our new notation for this general antiderivative is going to be writing this thing. So I'm going to pronounce it the integral of f of x dx. And it looks just like a definite integral, but there's a small visual difference. It has no limits of integration, right? So when you see an integral written there with no numbers on the integral sign, no limits of integration, then I'm calling that an indefinite integral. And unlike a definite integral, this quantity is not a number. An indefinite integral is an infinite family of functions, any one of which has derivative equal to the integrand, okay? So if I write something like the integral of f of x dx, I just mean the infinite family of functions, any member of which would have derivative little f. Okay, so that's what I mean by an indefinite integral. And this notation is motivated by the fundamental theorem. In fact, if we use the fundamental theorem, the second part in particular, the fundamental theorem says if you want to take a definite integral and evaluate it, this is a number, yeah, the definite integral of a function is a number. The fundamental theorem says you can take any member of this infinite family, you can take any member of the indefinite integral family and evaluate it from b to a. So plug in b, subtract, plugging in a. So that's why we're using the same notation for this notion and calling it an indefinite integral. It's indefinite in the sense that its value as a number is not specified until you specify these numbers a and b, okay? One last kind of part of this slide here, we can say something about it. If somebody writes something like the integral of f of x dx is equal to f of x plus c, they just mean that the derivative of capital F is little f. Right? So you know a whole bunch of things. Anytime you know the derivative of one function is another, then you know some indefinite integral. We were calling those antiderivatives in section 4.9. In fact, maybe I should say this, the notion of indefinite integral, let me write this down. Indefinite integral here in this current section, 5.4, is exactly the same idea as general antiderivative in section 4.9. All right, so if you go back and look at those homework problems you did in section 4.9, where I was asking you to find general antiderivatives, basically I could ask those same questions in the language of 5.4. I was asking you to find indefinite integrals. An indefinite integral is the general antiderivative for a function. If you evaluate an indefinite integral at endpoints, you get the numerical value of the definite integral. That's what the fundamental theorem of calculus says. Cool. So let's look at some of these things that we know. Here is the promised table from section 4, or page 403 rather. It's in section 5.4. So looking at some of these things, let me just randomly kind of pick one. Like let's look at this line together. So that's saying that the indefinite integral of sine of x dx is the negative cosine of x. And the reason that's true is if you take the derivative of the opposite of cosine of x, well, you would get minus sine x, you get sine x. All right, so you can pick any one of these lines. Let's pick on, say, this one. The antiderivative, or the indefinite integral of secant squared of x dx, is tangent because the derivative of tangent is secant squared. Yeah, so each one of these statements is really a statement about a derivative. It's telling you that the derivative of anything on the right, any constant, is the integrand, right? So if you pick any one of these things, the derivative of inverse tangent is 1 over x squared plus 1. What's this last one down here? Say the derivative of the hyperbolic sine is the hyperbolic cosine. All right. In addition to that, we also have some kind of more general properties up here. And this is saying that if you want to find the indefinite integral of a constant times a function, you can put that constant in front. You can pull a constant through the integral sign. That's true because that rule works for derivatives. Likewise, this formula, you want an indefinite integral of the sum of two functions. You can, sorry about that, you can find the indefinite integral of each one of the functions separately and add those together. That's true because that works for derivatives. Okay. In fact, the author, I don't know why, but this could also have said minus and minus. Not for products and quotients, because the product and quotient rule are more complicated than that, but for plus, minus, and constant multiples, those same differentiation rules hold for this indefinite integral because it's just the antiderivative, right? We talked about those properties for antiderivatives. Good. So this table looks familiar to you as long as your differentiation skills are sharp. If you've been differentiating enough in this course, then any one of these formulas doesn't look too intimidating. Every one of them is really just a statement about derivatives, but it's stated in this new language about antiderivatives. Yeah, so if you pick one of these things and you want to look at it, I'll highlight one more. That's just the statement that the derivative of secant is secant times tangent. Okay, the plus c everywhere is just indicating that it's the infinite family, the general antiderivative. Here, we can look at something that's not in the table. Maybe somebody wants me to verify the formula that the indefinite integral of the natural log of x is given by that expression, x times log x minus x. I'm not trying to say where this formula came from. If you're planning on taking Calc 2, you're going to learn some methods where you would be able to discover this formula. I could just give you this and ask you what it's equal to. That's a topic from Math 110 here at Humboldt State, Calculus 2. But here I'm not asking you to calculate or compute or find this indefinite integral. I'm asking you to verify this formula. So you verify a formula like that by seeing if the derivative of the so-called indefinite integral, in this case it's x log x minus x, well, plus any constant, that derivative should be log x if this formula is true. All right, well, we can take that derivative. We have to use the product rule. The product rule because of x times log x, and then we'll subtract the derivative of x. The derivative of this constant is 0. Right? So I'm going to make kind of quick work of this. So using the product rule on the x log x, I would get 1 times log x, and then plus x times the derivative of log x. Now I have to subtract the derivative of x, that's 1, and the derivative of the constant is 0. And if I clean this up a little bit, I get log x. X times 1 over x is 1. 1 minus 1 is 0. So there you go. That's how you verify a statement about indefinite integrals. As long as you can differentiate the proposed indefinite integral, you could always check. So actually, I want to say this is kind of a cool thing. You never have to get a statement about an indefinite integral incorrect if you're willing to check your answer. Anytime you're trying to write down some statement about, oh, the indefinite integral is this, you can always check your answer by taking the derivative of your this. It's supposed to be the integrand. Nice. Okay, let's do a bunch of examples. Your homework in the text, especially section of this 5.4, I just kind of gave you lots of skill and drill problems. So it's a chance for you to practice your anti-differentiation skills. Each one of these indefinite integrals, computing an indefinite integral are the directions. It just means find the general antiderivative, right? So that's the old way to ask that question. Find the general antiderivative. Compute definite integral, they mean the same thing. For a problem like this, in order to use our power rule, you definitely want to write that radical expression as a fractional exponent. So that's the 5/4 power of x. And now that indefinite integral, we just use our power rule, right? You take that exponent and add 1 to it. So 5/4 plus 1 is 9/4, and then you have to divide by that new exponent. So there you go. I'll leave it checking it to you, but if you differentiate this thing, you should get x to the 5/4 when you simplify it. So there we've computed an indefinite integral. Let's try another one. This is basically the same kind of idea, power rule, but we have to do some algebraic simplification to this thing. I have to take this t to the 1/2 power and multiply it through there before I can use the power rule. So I'm going to do that. T to the 1/2 times other powers of t, you add the exponents. So for example, t to the 1/2 times t squared is going to be t to the 5/2. Yeah, when I multiply t to the 1/2 by t squared, which is 4/2, you get 4/2 plus 1/2, that's 5/2. And so on. 3 square root of t times t is t to the 3/2. 2 times t to the 1/2. So that was just some exponent algebra, getting it ready to anti-differentiate, and now we use our power rule. So in each case, I'm adding 1 to the exponent. That's 2/2, if you like. And I have to divide by the new exponent, which I do. I like to prefer to multiply by the reciprocal. This one has a constant factor 3 there. I have to leave it there. These are the anti-differentiation rules. Bump that exponent up by 1, divide by new exponent. Last one's got a constant factor 2. Bump the exponent up by 1, divide by new exponent. When you're done, you get to the end, no more terms, add the constant of integration. Here, we don't need to, but let me just clean it up here. 2/7 times t to the 7/2. 3 times 2/5 is 6/5. T to the 5/2. 2 times 2/3 is 4/3. T to the 3/2. And again, I would ask you to check that formula with differentiation. Okay, differentiate this expression that we just derived with respect to t, and you should get, well, you'll get it in this form, which you could then factor out a t to the 1/2 and put it back in the original form. Nice. Seem familiar, these things? How about example C down here, throwing in some trigonometry? So to do this one, well, we take an antiderivative for cosine. So you have to think, well, what function's derivative is cosine? Sine. Sine has derivative cosine, and then we're subtracting what function has derivative sine. The opposite of cosine has the derivative sine. Yeah, add our constant, and we can clean that up. Sine theta plus cosine theta. Even though the directions to problems like these are saying compute the indefinite integral, compute the antiderivative, I don't know. Sometimes I kind of feel like, did I really compute this? I really just kind of wrote down some stuff I know. You know, when I wrote down this first sine theta, I wasn't really computing anything. I was just writing down the fact that I know the derivative of sine is cosine. So that's sort of handy. Here, we'll make one up here real quick. This was sort of from the table above, I guess. But what if I wanted you to compute, quote unquote, the antiderivative of, I don't know, the hyperbolic cosine of x. Well, you just have to basically say, like, do I know some function whose derivative is the hyperbolic cosine of x? Maybe you need to go look in a list of derivatives to answer that question. Depends on how much you differentiate. But if you go look in a list, or maybe you know it, yeah, you do know one. The hyperbolic sine's derivative is the hyperbolic cosine of x. So even though the directions to the problems are using this verb compute, and I don't mean to start a philosophical question here. I try to keep philosophy out of the math classes that I teach as much as possible. But I don't know. I don't feel like I computed anything there. I just feel like I wrote down some fact I know. But just FYI, the directions in your book are going to say things like compute the following indefinite integrals. So sometimes you're just writing down some fact you know. Sometimes you're doing something like this. This to me felt more like some computation. Anyway. Let's do some definite integrals, okay? Definite integrals. Definite integrals are done by finding, well, an indefinite integral, an antiderivative, and then evaluating it with the fundamental theorem of calculus. So unlike these indefinite integrals, sorry about the scrolling, I want to emphasize this though. Whenever I compute an indefinite integral, the answer is a function. It's really an infinite family of functions. When I'm computing definite integrals, the answer is a number. Right? We can interpret that number generically as a signed area, if you like, if there's no other context. It's the signed or the net area between the x-axis and the graph of this function. Okay, so, but how do you do it? You have to start with an antiderivative. The fundamental theorem says that you need to start with an antiderivative. So I'm just focusing my attention right now on this expression, and I'm term by term going to antidifferentiate it. Right? So I'm going to simplify this, I think, a little bit as I go. An antiderivative for 4x cubed is x to the fourth. If I put in some details, I added 1 to this, and then I divided by the new exponent. Well, 4 divided by 4 is 1. So I just simplified it as I went there. Likewise, the antiderivative for 3x squared is x cubed. The antiderivative for 2x is x squared. And then if I were finding an indefinite integral, I would add my constant here. I can add it. I actually will do it. I'm going to add any constant. But now I'm computing a definite integral, so I'm going to plug in the numbers 0 and 1. All right, so I'm going to write this out explicitly because I have a point I want to make here. So I'm going to plug in 1. So I get 1, take away 1 plus this constant. And then I'm going to subtract plugging in 0. So that would be 0 minus 0 plus 0 plus the constant. So notice that constant shows up once here with the sign plus because we're plugging it in for the upper limit. And then it shows up here and it will have the opposite sign because we're subtracting it. So it will cancel. The constant cancels regardless of the rest of the details of the computation. In fact, that's always going to be the case. So because of that, because this constant will always cancel, in doing a definite integral, I always will take c to be 0. I don't have to worry about adding that constant. You can if you want to. But when you go to plug in and then subtract the upper limit minus the lower limit, the constant will always cancel. You could have just used the antiderivative part without it. In other words, you can pick a specific member of the antiderivative family, and why not pick the member where the constant is 0? It's the simplest one. Cool, so from now on, I'll do that. When I'm computing a definite integral, I won't write this plus c anymore. I had some more arithmetic to do here. I think this thing ends up being 1. Okay, so again, what does that mean? I don't have a picture of this function ready. We could switch over to Desmos if you want, but I know that there must be more area above the x-axis than below the x-axis for this function over that interval because the integral was positive. This might be the area if it was always greater than or equal to 0, but we know that it has to be above less than or more than it's below because the net area was positive. Okay, let's do another one. Let's compute the definite integral. We need an antiderivative. Going to do it term by term, an antiderivative for e to the t. Maybe you should stop the video and do this before me, and then just turn it back on and see if we write the same thing. So my antiderivative, well, the antiderivative of e to the t is itself. The antiderivative of 1 is t. because the derivative of t with respect to t is 1. I'm not going to add any constant here because I'm doing a definite integral, so I evaluate. So you see why this evaluation bar is handy, because I have to focus all my attention on this antiderivative. I can't find the antiderivative, plug things into it, and subtract all simultaneously. That's too much multitasking. So this evaluation bar, it's a stopover point. Okay, I got my antiderivative, and now I have some room to write down, plug in the upper limit, plug in the lower limit. Carefully evaluate these. That's e plus 1. E to the 0 is 1, so it turns out to be e. Okay, this one we could really quick. I've got enough room down here. I can graph this function without Desmos. E to the t plus 1 looks like the exponential graph shifted up by 1 unit. So that would be the y-intercept 2. That's my t-axis. Okay, we went out to t equals 1. So we just computed that area. That area is exactly equal to e, or approximately, what is a decimal approximation for e? 2.718 or something like that, but its exact value is e. So I know that's an area because this function is non-negative over that interval. Nice. Let's do one more. Same kind of ideas. Stop the video, compute this antiderivative, and evaluate this thing before me. All right, so taking term by term antiderivatives. What's an antiderivative for 2 times x cubed? Well, it would be 2, add 1 to that exponent, divide by the new exponent. 6, add 1 to the new exponent, divide by the new exponent. This one, 3, antiderivative for 1 over x squared plus 1. Maybe you recognize it. It's the inverse tangent. So when you're doing your homework, if you get to a point where you're like, hey, how do I antidifferentiate something like 1 over x squared plus 1? If it doesn't occur to you, then go check that table. Go check that table on page 403, because that's your table of antiderivatives, and you'll see that 1 over x squared plus 1 in there. This 3 was just a constant multiple, so it stays in front. Okay, so it's arctan is the antiderivative, and I need to evaluate that from 0 to 2. I'm going to simplify my fractions as I go here. 2 times a quarter is a half. So I've got a half of 2 to the 4th. 3 times a half, 6 times a half is 3. So that's 3 times 2 squared, plus 3 times the inverse tangent of 2. I'm just going to put that. That's calculator work. And now I have to subtract. Always use a parenthesis when there's more than one term. Plugging in x equals 0. Well, 0 to the 4th is 0 minus 0 squared. And then the arctangent of 0 is 0. I know, without a calculator. You can check it out, though. The inverse tangent of 0 is 0. So this thing ends up being, what, 16 over 2, that's 8, minus 3 times 4 is 12, plus 3 times the, I have to figure out this on my calculator, but 8 minus 12 is 4, negative 4. So here's an exact answer. An exact answer to that expression is given by negative 4 plus 3 times the inverse tangent of 2. If you get out your calculator, which you could have done the inverse tangent of 0 with a calculator too. I just knew that one was 0 because the tangent of 0 is 0. But I don't know the tangent of what angle is 2, so I would do this on my calculator. I'm definitely wanting to be in radian mode, and I'll write this down just so you can check it. I did it before I started the video. It's approximately negative 0.67 or negative 0.68 if I'm going to round like that, but I wrote 5 decimal places. Okay. And so what does that mean? Well, if we interpreted it as a net area, if we interpret this number as a net area, it means that there must be more area below the axis than there is above over that interval. All right. I've got a picture of this function down here for us. That's what the function looks like over the interval from 0 to 2. And you can see that there's some area above the x-axis and there's some area below the x-axis. And this integral calculation gives us the net area. So this part that's below is slightly bigger than the combination of the two parts that are above. The net area is negative. Or if we wanted to switch the context, so let's say, this will be the last thing I say in this video. If I wanted to think of this thing as the velocity, if this is the velocity of a particle moving along a line, Yeah. Then when that velocity is positive, the particle is moving. So this would be this is a graph of velocity, not position. So when the velocity is positive, the particle is moving in the positive direction. And now the particle started moving in the negative direction because the velocity is negative. And now the particle is moving in the positive direction again. All right. So if you kind of think about it over time, for a while it was moving to the right, and then it was moving to the left, and then it moved to the right again, if positive direction is to the right. So what this number would mean in that context is it's not distance traveled, but rather it's displacement. So this object ended up slightly further to the left of where it started because it moved left. The distance that it's moving left is this yellow shaded area more than the distance that it moved right, which would be represented by the blue shaded areas. Okay, I hope those were useful examples. Thanks for listening.